Good afternoon, everyone. We'll start another Kent seminar. Today we have Professor Songsu Son from Liberty University. Before we get started, maybe Professor Alkali wants to come here and say some words for Professor Son.
It's always a pleasure to see you. I'm glad that I had him at. Oh, do I need a microphone? Okay, sorry. I'm so glad that you've been able to come and be with us today. I very much enjoyed my interactions with him during his PhD. It's just an amazing, and I visited with him also when he was in Abu Dhabi. Dubai. That's just
close.
Very close. But all I know that he took me for a lunch, and I didn't know if it was in Dubai or Abu Dhabi, but it's one of these two places. He did an amazing job while he was doing his PhD. Actually, he was. I don't know if you're going to touch on this, but a little bit. And he worked also on a project that we had for the IDOT at that time that we were looking into everything for new surfaces for the overlay, looking into the noise, the micro, the thin overlays, the use of, if you remember, we were using the chips on the asphalt for the first time. But among all, I mean, it's just, you could see how much I'm excited about having you here, because it was just a pleasure to have you back in Champaign. You can see that his politeness is definitely, I'll give him number one among all my students. So you're gonna see that in a minute, right? So please join me to welcome.
So before Professor Son gets started, I'll just give his short bio. Professor Songsu Son is now an associate professor at Liberty University. His research focuses on sustainable road materials, innovative technologies on road construction, and connected and autonomous vehicles in transportation systems and infrastructures. Dr. Son also dedicates his efforts toward international development, having worked previously in the United Arab Emirates, Morocco, China, and South Korea. He serves as a technical committee for the World Road Association and was a founding committee member of the Chartered Institution for Highways and Transportation in Dubai. Dr. Son earned his PhD from the University of Illinois Urbana-Champaign back in 2014. And let's give him a round of applause.
Good afternoon, everyone. It's my great pleasure to be here. And then, this rental feels like, my second hometown. So I spent my 20s, 30s years. And I have a lot of the good memories here, as always with Professor Akadi. So he always encouraged me that whenever I had up and down, and then so sometimes we are going through the darkness, but he always gave me the good advice to challenge myself and then grow through the difficulties and hardships. So thank you so much for inviting me. And then today I'm going to talk about some of the research that I'm doing at the Liberty University. This is the Liberty University campus in Central Virginia. So we just started the new civil engineering program. So it's in 2019. So I was hired as first civil engineering faculty. So we went through the ABET accreditation, developed the civil engineering curriculums, and then we just submitted ABET accreditations package last semester. So I really enjoyed to develop the new civil engineering programs here, and also some of the research capability and the potentials. So today, well, before I talk about the topics, I'd like to introduce myself. Well, the people, the students at the Liberty University calls me the waymaker. So I'm in transportation engineering. So I always love to be called the waymaker. So long journey to become the waymaker. And I was born in South Korea, and then I did my bachelor and master's in Seoul. And then I moved to the States for my PhD here at the University of Illinois at Urbana-Champaign. So during my master's, I actually did my master in traffic engineering about railroad and then the metro system. And then I took a lot of the economics class to find the optimum fares for the new line of the metro systems. And also you call this the only service of this network. And then from the 2002 to 2005, then I worked in the Ministry of the Transportation in Morocco, and then I taught the National University of Architecture in Morocco as well. It was my first time to work in outside South Korea. So I learned a lot. So it was blessed time with a lot of the people around. So one of the projects that I was serving as a PI is the signalized intersection, the roundabout analysis, and the safety improvement. And then after that, I found myself I need to continue the graduate programs, and then I spent about 6 years here in Seoul, and then completing my PhD. And then after that, I loved the Middle East a lot, and then moved to the United Arab Emirates. So I taught at the American University in Dubai for 6 years till the 2021. And then Dubai is a really nice place to learn a lot of the high technology. So we have the flying taxi over there. And then this is the longest driverless metro system in the world. And also, I'm not sure if you have heard about the Hyperloops. So there's a Hyperloop project between Abu Dhabi and Dubai. So the one thing that I love, I'm still young, I believe I'm still young, but there's a lot of things that I can learn. So that actually gave me a lot of good memory to challenge myself to grow in academia and also in the research. And then, so from the 2017 to 2021, almost every summer, I had the opportunity to teach in China. So, and then in 2021, we came back to the States, and then I joined the Liberty University to develop the civil engineering program. I love to travel here and there, and then I love to learn the new cultures and then talk with people from the other, the different countries. This is the transportation labs at the Liberty University. So I joined the Liberty University 2021. And then I had, kind of the opportunity to set up 3 different labs. So this is an asphalt lab that we have a full kind of the scales of the pavement performance test with the AMPT and the auto extract, and then the Hamburg wheel tracking test, and then binder test equipment with some environment chamber. And also we have, this is the volumetric rooms, and then this is mixing stations that we have. And then I'm in charge of the traffic engineering part as well. So we purchased the traffic simulator. So we have this research about autonomous vehicle. So one of the students, or 2 students in my groups, are running the the traffic simulation to see how the autonomous vehicle is moving the intersection and the roundabout. And then what is the benefit of having the higher, the penetration of the autonomous vehicle on the roadway? Do we need to, do we need to prepare something, and then will we have the, more congestion or less congestion as we have more and more autonomous vehicles? And also, that we have the autonomous vehicle set up here in the driving simulators, and then we just let the driver sitting in the seat, and then change the environment to see the how, that this driver actually respond to the certain instance. And then we have the cameras around, and then we have some, the analysis software here to capture humans' response to the autonomous vehicle systems. And the one on the right-hand side is for the trucks, heavy vehicle. So emergency vehicle or the bus, and then we can run the simulation on the different setup of the traffic simulator. And also we have the four the drones, and then we use this drone to monitor the traffic and then get some the image for the pavement surface. And also one of the projects that I'm working now is using these drone systems to detect water source in the underdeveloped country. So we sent some students over the summer to the underdeveloped country to help the people to find a good clean water source. And then one of the challenging was how to find this water source. And then very traditional one is put the electric bulbs on the ground to send some signal to find the water source. But if you have the huge space, it's really hard to find the potential point of the water source. So what we are doing is we have the thermal camera on it, and then fly the drones over the land, and then measure the thermal data every 2 hours to see the temperature variation. So assuming if there is a water source under the surface, probably heating and cooling rate might be different from the dry area. So we try to, it's not to detect the water source itself, and then trying to narrow down the potential point to drill the ground to detect the water source. The current research topic, and they're using the asphalt facility, and then I'm working on the repurposing the waste plastic as a fibers in asphalt pavement. So there is a dry process and a wet process. It has been investigated for a long time to use the waste plastic as a modifier for binder, or the replacement of the fine aggregate as a dry process. But our approach is to use this one as a fibers, and then I've been working on the fiber reinforcement, the asphalt pavement. So we try to use this one to reinforce the cracking resistance, or improve the cracking resistance in the asphalt pavement using the waste plastic fibers. And then this is the one that I explained. So this is the autonomous vehicle traffic simulator. And then we figure out what is the impact of the autonomous vehicle at different automation level and then different penetration rate on the roadway in terms of the traffic flow. And also this one is for the pavement surface life. So if you have the autonomous vehicle, it has kind of the limited wandering systems. And then we try to figure out will this autonomous vehicle kind of extend the pavement surface life or will damage the pavement faster. So so we can capture the location of the vehicles under the human driving, the setup versus autonomous vehicle setups to see this data. And also, yeah, this is the one that we are currently, doing in the lab and also in the field using the thermal data to capture surface temperature variation. And then the last one is we are also working with the electrical engineering, the student, to use the piezoelectric sensor to harvest the energy and also get the real-time traffic data. So this is what we developed last year. So 4 electrical engineering students involved in this project. and then one computer science student developed a code how to actually collect this traffic data through this sensor and then send to the cloud service real time, and then we can check the types of the vehicles, and then using this voltage change, and they use this voltage change to the weight information, and it's based on this wave, the shape of this wave, and then we can categorize or classify the vehicle types, the real time. So this is one of the ongoing projects. So now I'm going to talk about the main research that we are doing at the Liberty University. So we try to repurpose this waste of plastic. So over 40 million tons of the plastic waste in the US is being produced, and then at least 80% of this waste, plastic waste, is being sent to the landfill. So only the little less than 10% of the waste plastic is recycled. We try to figure out how we can recycle this plastic waste. So in the asphalt pavement industry, we try to people try to use this one as a dry and a wet process. And then, but there is a pros and the cons when we use this waste plastic as a wet process and dry process. If we use this waste plastic as a dry process, and then there's some kind of the challenge to determine the size of this the plastic, and also if we use this one as a wet process, there's kind of segregation problems, and also it's really hard to store this one in the plant for a long time because of the separation of these materials. So this shows the typical types of the plastic waste. So there are low density polyethylene and the HDPE, PP, PVC, PET, and the PS and nylons. They're on the melting point and then sources. So we try to look at the melting temperature because asphalt paint, the materials are being produced around 300 to 350 Fahrenheit. So when we use this waste plastic as wet process, and then we have to choose the materials waste melt at the mixing temperature, but for dry process, then we pick the types of the plastics that has a higher melting point than the mixing temperature. So since we try to use this waste plastic as fibers, and then we pick these two waste plastic types, which is a PET and a nylon. So basically, it's two different projects in our research team. So we actually try to recycle the wastewater bottles for PET, and also we found there are a lot of ocean waste. Okay, fishing net. Okay, fishing net actually damage the ocean animals and the ocean environment. So we try to recycle the fishing net. So materials type of the fishing net is nylon. So we try to use both of them as a fiber to reinforce the cracking resistance of the asphalt pavement. As I explained earlier, and then we have the two different types of the process to recycle plastic. But the common drawback of this production of this or post-process of the recycled plastic is it produces hazardous chemicals and then toxic fumes, especially when you melt, then make the pellets to be used in the production of the asphalt materials. So typical, the pelletizing process start with collections, inspections, and then chopping, and then separation, drying, and then melting with the heat and pressures, and then molten, and then it's through this one to make the pellets. The problem is these stage or the steps require a lot of the energy consumptions, and also because it's melting, the plastic at a higher temperature, it emits the fumes. So even for the dry process, and then most common, the application of this waste plastic into the through the drying process still make the pellet. shapes. So which has a higher melting temperature than the other, the types of the plastic used in the wet process. So the both process actually require the melting process to make the pellet shapes. So we try to avoid this kind of the steps. Instead, what if we just chop it and then make the fibers types without actually this post-processing to make the pellets types of the plastic. So what we did is we used these bottles and then just shred it and then make this shape of the plastic fibers, and then use this one to improve the asphalt, the performance in terms of the cracks. So this is one of the projects that I was working, which is ICTR 27-42, development of the required sustainable materials. And one of the mixture that we had was a fiber reinforced the asphalt materials. So when we use the aramid, the fibers, and then it actually improved the fracture energy by the 57%. So there's a kind of possibility to improve the fracture energy by using the fibers in the asphalt materials. So, and then as you can see here, and this fiber actually reaching the cracks when there's a crack propagation. So we try to use this fiber, chopped fibers, to breach the cracks during the crack propagation. The very first thing, the selection of the types of the plastic for fibers, and then based on the melting point, and then we take this PET plastic, and then we fabricate to make the 20 by the 20, the 5 by the 20 millimeter of the size, and then also we pick this nylon, which is from the fishing net. So when you chop it, and then it looks a little bit different from this PET types of the waste plastic, but we don't need to actually cut by width. So we just cut this the fishing net into the 17 millimeter of the length. So and then we use these two different types of the fibers in the asphalt mixture. So this shows the scenario, the types of the plastics and the dimensions and the contents. So we had a control mix without any fibers, and then PET with the thickness of which is the width of this fiber of 5 millimeters, and then 2 millimeters and 8 millimeters with the different thickness of these fibers. And also we had 3 different lengths of the fibers from the 10 millimeter, 10 millimeter to the 13 millimeter. And also we had various, the fiber contents to see the impact, the effect of this, the various fiber contents into the asphalt performance. As you can see here, then we fabricated this one manually, so we didn't use a shredder because it's really hard to control the shape of this one. So I think over 10 the undergraduates should actually sit in the classroom and then just use this one. So they had a heart to recycle some materials, and then they collected all of these bottles from the dorms, and then huge bag of this plastic bottle in the classrooms, and then we have this kind of things. And then so we use this one, and then before we put this plastic into the asphalt mixture, and then we try to figure out how it performs at different level of the temperature, and then different level of the heat conditioning. So when we put the PET fiber into the oven, and then we heated up this one for 8 hours, and then even up to the 24 hours, and then we apply the tension test. As you can see here, as over the hours being heated in the oven, and then this maximum force to the failure actually dropped by about 20 to 30% because, and also it changed the shape. I'm not sure if you have seen this kind of things. If you have the broken chairs, legs, and then we can cut the plastic bottle and then put it into it, and then apply the heater, and then it actually grabs this chair legs to fix it. So And then it happened the same here. And then when you put this one into the oven over a long time, and then it actually changed the volume. So the reason why we did this one is to see what is the surface area change over time, because it actually determines the contents of the asphalt binder. So if we have a larger contact area, so we did this one. So as you can see here, the area also changed or reduced by the 25% after 8 hours. So we put the nylon fibers, which is from the fishing net, and then put into the oven. But this nylon didn't change the property in terms of the maximum force, and also the length didn't change much over hours. So, and then using this one, and then we put this one into the base asphalt mixture with 9.5 millimeter max negative size with Pg64 - 22, and the AC contents of the base mix was 5.6%, and the mixed temperature is 315 Fahrenheit, and the compaction temperature is 290, and then it has 25% of the lead in it. And then we actually made the lead produced, the lead compacted, and also we sampled the materials from the plant, and then we compact that one in the lab. So we have the two set of the materials, and then we set up the 0.2, 0.4, 0.6% of the plastic, and then we run the GMM, the test. So this is the nylon fibers before we put this one into the mixture, and then PET fiber shape, and then this is lead produced, lead compacted materials. And then what we did is we put the fibers during the, and then we poured this aggregate into the bucket, and then put the fibers, and then the mixed before we put the binder on it, okay, to make sure this fiber is well distributed before we add the binders. And then for this lead plant produced one, and then we had to just put the fibers into this pre-blended materials. Then, we blended thoroughly. So we compacted it to the 160 millimeter of the height to make the SCV samples, and then cut it into the half, and then put into the environment chamber to condition at 3 different temperatures, 25 and then 1 and minus 12 degrees Celsius. We ran the test in the AMPT machine that we have. And then for the 25 degree Celsius, and then we use a 50 millimeter thickness of the specimen with LED control, load line displacement control, and the loading rate that we use is 50 millimeter per minute according to the IFIT specifications. And then we look at the GF fracture energy M and then flexibility index. Same for the 1 degree Celsius, and then we try to keep the same thickness of the specimen to minimize the geometry kind of dependency of the fracture energy. And also we apply the 2 millimeter per minute of the loading rate, and then we look at all the same the fracture energy M and the flexibility index. For minus 12 degrees C, there is a Ajoto T394, which is standard SCV fracture test at the low temperature. And that's why we picked up minus 12, since we use the Pg64 - 22, and then 10 degree above this lowest lowest highest temperature, right? 22, yeah. Lowest temperature is the one that we use. But this standard use 25 millimeter of the thickness in the specimen, but to be consistent, we use the 50 millimeter thickness of the specimen. And then loading rate, we start from the very slow loading rate and the high loading rate, but this specification use the CMOD control that actually gives the the kind of the crack propagations. But if you apply the LED control test and then at the low temperature, it's really hard to control gradual propagation of the cracks. So we had some trial and error, and then we decided to use a 0.3 millimeter per minute, the load line displacement controlled. We look at the peak load, fracture energy, and the flexibility index as well to figure out what is the impact of these fibers into the asphalt cracking performance. So this slide shows the result of the fracture energy. This result is from the 5 millimeter by the 20 millimeter of the PET5 dimensions with 0.4% of the fiber contents. As you can see here, as we add fiber, PET fiber, and they improve the fracture energy at both 25 degrees C and the minus 12 degrees C. Same for the nylon fiber. So it actually improved the fracture energy by about the 50% at 25 degrees C, and then for the low temperature, it improved the fracture energy by 130%. It's a huge improvement of the resistance. We look at the FI value as well. So as you can see here, and then in both the temperature, we see the significant improvement of the flexibility index. So this is the fracture energy versus percent of the plastic that we use. So 0 is control without any plastic, and then 0.2%, 0.4, and then 0.6. As you can see, and then fracture energy increase and then start to decrease here. So this is very common when we have this kind of the composite materials, when we add additives more and more and more, at certain point of the critical volume fractions, as you add more and more, it actually start to make this kind of the materials weaker and weaker because of the connection of these additives that makes that creates some certain kind of the wood surface. We observed that this one here in the fracture energy. So one of the papers or research done by Dr. Hyunjun Yu in 2014, he used a PET plastic, and then he found 0.4% is the optimum because he found the same trend of the fracture energy increase and decrease. But we try to look at a little bit more because this is a kind of a bulk fracture or energy response, including pre-peak and the post-peak. And then we zoomed in and then look at the post-peak fracture energy because these fibers is actually the bridging, the crack. So we try to zoom in the post-peak part. And then when we zoom in the post-peak fracture energy, as we add more, the more and more plastic, it continuously increases the fracture energy except the 25 degrees C. So there's a question mark, and then why do we have the different kind of behavior between 25 degrees C and the low temperature? So we look at this fiber failure side. So at the low temperature, when you look at the fiber types here, and there is a Sharpie, which means this fiber was broken during the crack propagation, which means the fiber holds this material together, and then it actually breaks when the crack actually forced to propagate. But in the 25 degrees C, even at the higher loading, the rate, which is a 50 millimeter per minute, and then we found most of the fibers had its own original shape because it's slipped out. Although we apply the high loading rate, and it's not high enough to break the fibers. Instead, the fibers slipped out. So that's why. And then at the higher temperatures, and the effect of this fiber was not very much pronounced and then visible, although it improved the fracture energy in certain way. So, and also look at this surface again, and then you see the aggregate was broken at a low temperature as the crack propagate, and then you see these fibers, the breakage. And also at the high temperature, you see a lot of the fibers kept the original shape after crack propagation is done. Okay, so this shows the nylon fibers. So it looks like very hairy type, so we have a lot of fibers on it. So dimension versus the fracture energy. As you see here, and then as we increase the length by keeping the width of the fiber to the 5 millimeters, and then increase the length of the fiber from the 10 20, and 30, and then put into the mixture. And then it shows as we increase the length of the fiber, and then it actually increase the fracture energy, which means the deep fibers, the longer fiber can resist these propagations better than the short fibers. And then we did the same things, keeping the length of the fiber 20, and then increase the width of the fiber from the 2, 4, and 6. But you don't see the continuous increase of this one, because think about if you increase the width, and then it actually decrease the aspect ratio of the fiber. So as you have the wider and wider fiber, it actually create a weaker surface more and more and more. So that's what we found. And also, when you look at this the load displacement curve, and then one of the things that I want to emphasize here, so this black one is a contour without any fibers. And then when you add PET fiber at the low temperature, and then you can see the significant change on the tail part. And the nylon has a huge improvement of the tail part, which gives us additional fracture energy to completely break this specimen. To see what we observed in the lab is it feels like as we add more and more fiber, and then this material becomes kind of softer and then loose, and then sometimes it's really hard to hold the shape of the specimen. So what we did is we just made a 115 millimeter height of the specimen, and then put into this cantorless drums, and then rotated without steel balls to see the durability of these specimens. And then the contour mix shows the material loss of the 5.8%, but PET fibers has almost a similar, the materials loss, although this picture we picked the worst specimen here. And then nylon fibers, as you can see, it's hairy, but it lost a lot of the materials. So balanced mix design has a kind of in Virginia has a specific criteria. So this material loss should be less than 7.5%. Okay, so the nylon fiber is out in terms of this specs, but we use only 0.4% of the nylon contents for these nylon fibers. So the conclusion here, and then recycling the waste plastic as fiber is very promising to improve the crack resistance if we choose the right dimension of the fibers and the right contents of this fiber in the mixture. And also, the impact of these fibers in the fracture energy is more pronounced in the post-peak area, because it holds these materials kind of the failures after the peak load. And also the temperature. So at the higher temperature, which is 25, intermediate temperature, 25 degrees Celsius, and then we saw that this fiber has the slid out, while at the lower temperature, we observe the fiber breakage. So, but in asphalt, we have the fracture failure temperature, the cracking happening in the low temperature usually. So that's why we see the fracture, cracking resistance at the low temperature or at the room temperature with a higher the loading rate. So it behaves differently at different temperature. Plastic fibers, as you can see here, I didn't mention that one. So as we add more and more fibers, and then it actually shifts the critical, it's not critical, the displacement at the peak load, which means it delays the failures. Okay, it actually fails at the higher the displacement, but still it drops. When you use the nylon, it drops the peak load, but it improves the crack resistance capability after the peak load. Okay, so compared to the PET fiber, nylon fibers shows the higher fracture energy when using the asphalt pavements, but till we use only one content, and then one types of the nylons. But what we are going to do is we're gonna look at the different source of the fishing net. So probably we use the brand new the fishing net, which costs about $20 in Amazon, and then we chopped it. So this is a new nylon. But the next step, we're gonna actually collect waste fishing net, which is old waste, and then probably we'll have the different, the reaction to the sodiums, and then so we're gonna try to use the real waste, the nylon into the pavement to see how it performs. And also fiber shape and then volume fraction is important. And then one of my the PhD student is working with the professor in the material science, and then we try to determine what is the optimum, the volume fraction of the fiber, and what is the right, the dimension of the fiber using self-consistent mathematical model. So in the material science, this model has been used for a long time. So we try to use this one to determine the volume fraction of the fibers that perform the best. Dispersion and the plant application has been the issue whenever we use the fibers. And then I remember 10 years or 15 years ago, when we produced this select fiber reinforced concrete, asphalt concrete, and then put into the Chicago area. And then it was really hard to produce this one in the plant. So dispersions and then application of this one in the field is challenging. So we try to figure out how we can guide field or asphalt contractors to use this one in the field. And the optimum contents is one of the challenges that we need to determine and find. And then PET fibers, and then we use only one source of the plastic bottles, which is Deer Park water. So it has the thickness of the 0.28 millimeter. But if you use the different types of the water bottles, and then you might feel a little bit thicker. So we try to use the different types of the plastic bottles into this asphalt. And the optimum nylon fibers, as I said, different types of the fishing net has different mesh patterns. And then we try to figure out the different types of the meshing patterns. And they use that one in the asphalt plant and to see how this pattern of the mesh gonna affect this cracking resistance improvement in our research. Right. So I like to acknowledge the Center for Research and Scholarship at the Liberty University. We don't have the external funds yet, but the internal funds support actually our research. So, and also we had all of the materials from Oxley Materials in Virginia, and then they were, helping us a lot. And also researchers. So these are the heroes to make this, research report. They seems like happy to play with these black materials. Right. This is my research reference, and then thank you for your attention.
We have some time for discussion now.
Yeah, thanks. Great presentation. And can you go back to the slide where you have the first FI and fracture energy results?
Probably this one.
Yeah, exactly this one. So it was interesting. It seems at 25C, the nylon had a much better fracture energy than PET, but FI actually was lower in 25C, which at intermediate temperature seems to me it's very brittle material because it's actually reaching the peak and then having a very high slope as it decreases. And then I noticed your Cantabro, you also had the worst performance for that one, which also is a room temperature test. So it seems in room temperature, this one is having some kind of brittle or losing its flexibility in a way, and also having graveling problems. I was thinking maybe the binder content is low in this mix. Did you try any redesign or looking at the?
That's good question. So for for now, we didn't touch any mix design yet. So the next step is we're gonna, look at the VMA and the volumetrics to see as we add more and more dry materials, which is fibers, they create surface area more and more. Yeah, definitely we need to consider to add more binder. But when you use these aramid fibers, and then they said we don't need to touch the volumetric or mixed design. It's a small amount of the fibers. So, but 0.4% seems like we need to touch the binder contents as well because it makes the materials drier when we add these fibers. That's the point. Yeah.
Questions? I have
Yes.
one question. When someone. Oh, okay. Just very quick question. Did you try to use these plastics in mixes that usually require the use of fibers like SMA and borrows?
No, the purpose of this fiber in the SMA is to prevent the drain down,
Yeah.
right? To hold binder. So the fiber used here is to hold the cracks actually. So yeah, so it's a completely different, the purpose of using the fiber. So we haven't tried this one in the SMA mixture. I don't think these types of fiber can prevent the drain down much. Okay. Good question. Yes.
Thank you for the nice word. It's great to see you. I have two questions. The first one is, so the thought is you're gonna use plastics that are recycled. You don't necessarily know the degradation level of that plastic, right? Maybe it's out in the field and showed us as the hours increase, high temperature. So I was wondering, what are your thoughts when you're gonna be incorporating potentially like different plastics, different degraded levels? As you're trying to make sure
Yeah.
and improve the mix. And then the second question is, I think it's good to control the aspect ratio, but the mass scaling of that gets difficult because then you want the size specifically versus when you mass produce it, as you mentioned earlier, it's gonna be different. So I was wondering, what are your thoughts on these?
That's a good point. So for the first one, what was the
The
first?
degradation level, how are you gonna account for that? Because you will change the plastic types, but maybe the level of how they can help the mixture will vary depending where they came from and how degraded the plastic has been out in the field.
Yeah, so this is a kind of the early stage of the research, and then there are a lot of things to take care of, so in the industry, gonna have the different, the opinion for this one, the ones if it's easy or hard to process these fibers, or chop in that way, and then is it easy to control the shape of this one or not, and then, and also we didn't use the shredder, so actually I went to the Walmart and then you see the different types of shredder, and then they shows the length dimension of the shredded pieces. And then even this shredder has a different, the length and then the width after, you shred it. So that's why at this stage, and then we try to see what is there any kind of the impact of this dimension or aspect ratio into the performance or not, and then we try to explore what industry people are gonna talk about this one to address, and then we might have the several options to provide to the industry, and then get the feedback, and then what is practical, what is not practical, and then to tweak our application for this the industry. Yeah, that's a good question. Yeah. Yes.
Hi, thanks for the nice presentation. Can you go to the slides of the fiber failure for the low?
Which slide?
Next slide. Yes, this slide. So for the fiber reinforced concrete or cement concrete, we usually see the fiber pull out instead of fiber break. As the strength and modulus of fiber is usually significantly higher than the material. But here in the low temperature, we can see the fiber breakage. So I wonder whether the temperature will significantly affect fiber properties. And this factor will affect the different fiber failure? Or it's just the different fiber failure is caused by the material or by the temperature?
Yeah, that's a good question. And what the student is doing this week and next week is we try to see the frictions between the binder and the fiber at a different temperature. We couldn't find the specification for that. What we are going to do is we're gonna have those tubes and then fill the binder on it and then put the fibers. And then so put into the different temperature and then pull it to see the to see the friction between the binder and then fibers, and that will explain what is the kind of governing factor that makes this fiber broken at different temperature, or probably the types of the binder may affect this one, or types of the fiber also affect. I don't see, well, for example, for the nylon fiber, I don't see any breakage of this nylon, even at the low temperature. So probably, and also aspect ratio is also important. So if you see the very thin and the long one, and then each two break, but if you have the wider one, and then if you apply the tension here, it's hard to break. So this shape affect that's kind of the breakage of this. Yes.
If I may ask a silly question, I also had a question regarding this breakage. So did you see the binder cracks of the specimen showing significant different sort of modes of cracking, like more sudden or more gradual? Would that have an impact on the loading into the fiber? What I meant is actually, I assume, again, non-expert, right? Like you gradually crack.
Yeah.
Then there will be more pulling opportunity to pull it out, rather
Right.
than you have a sudden cracking under low temperature. That might have a huge load onto the fiber.
That's a really good point. As I said earlier, and then we apply the load line displacement control for low temperature. So that's why we had a trial and error, because sometimes it breaks suddenly, and then sometimes it breaks gradually. So, but H2T, the 394 is a CMOD control that actually gradually, pull this specimen apart. So, and then we see the gradual propagation of the cracks. And then in that case, that even at the low temperature, we might see the slip out or pulling out at the even low temperature when we see the gradual propagation of the crack. But under the LND control that we control that is the load line displacement, and then we couldn't avoid this kind of the sudden failure of this specimen. So that's why right up to the point that the cracks start and then propagate suddenly, and then it's a higher load stress is applied to the near crack tips, and then it's kind of impact, and then just break the fibers and close the crack tips. So probably not very obvious, and then the further away from the crack tips in that case. Yes.
May I ask a follow question? When you see the sudden failure, have you ever seen the section of, so is there a lot of fibers in the section or not? The fiber distribution will affect failure.
Right. Yeah. So the first point, when we applied high loading rate for the -12 under the LNT displacement, and then we couldn't capture the data point post peak because sudden failure, and then we had just a 2 or 3 data point which doesn't show the the good the curve at the peak. So that's why we couldn't capture this one. So that's why we actually adjust the loading rate to capture that part. And also second one, I have something to tell. Yeah. Second one was. Yeah, I would, yes.
Just a follow-up. I think a simpler way to think about this is like if we go back to the glass transition temperature slide. There was a slide we showed the glass transition temperature. So yeah, the more we go with the low temp, the more we're reaching to the glass state, or where like the elastomer is changing to be more rigid or more glassy. And that explains why the fiber is
Yeah.
broken.
So PS has a, glass transition. So certain types of plastic has, the lower glass transitions, kind of the point. So that's why the PET has, changed its property over, temperature, while the nylon didn't actually change its property over time at a different temperature. So it's kind of shows, although both of them are not melting at certain temperature, and then, but if heat is, temperature is in the glass temperature, transition temperature, it may change the property of the plastic. Yes, glass transition temperature is also one of the
Sorry,
important.
so you heated the plastics for 310?
Yeah.
So is there a reason why you picked this temperature?
It's kind of the range of the mixing and then compaction temperature.
Okay.
Yeah, Fahrenheit. Yeah, so that's why if you put the fibers and then mix it, and then the drum mixer has this temperature, and then we keep this one in the silo. So that's why, so it will change the shapes when we store that one in the silo.
So thank you again, Professor Son, for the nice presentation. Thank